now let's welcome our second speaker, Iris Rammelmüller. So Iris is a PhD student at the Alpen University in Klagenfurt. She also holds a bachelor degree of mathematical science and also master's from the University of Salzburg. And she told us before that she's highly interested in multi-perspective research that combines different mathematical subdisciplines. And today she's going to tell us a bit how she follows this interest within her PhD work. Yes, and I'll already hand over to you, Iris. So her talk will be about computationally efficient pollutant dispersion calculation. So thank you a lot.
Thank you so much. Thank you. So first of all, thanks to the organizer for this amazing event. It's an honor to be here. Today I will give you an insight into air dispersion modeling because this is quite important for the future. So I have the same problem, I see. Okay, short moment. Okay, it's fixable. Yeah. Okay, hopefully now it's better. So sorry about that. Well, as I said, a little insight into this topic. I'm searching for my PhD. So what are the mathematical equations? What are the physical laws? And of course, what are the computational burden for the implementation of the models? So I will start at the beginning to introduce a little bit into the different influences of air dispersion modeling. And afterwards, I will talk about two different models I use in my work. So the Gaussian plumb equation and the stochastic Lagrangian particle equation. The goal of calculation dispersion is to predict or diagnose a concentration profile from a source to a distance away. So for better understanding, we take a closer look at the first bubbles in detail. So starting point is the topography. So in general, it describes the study of the different forms and features of land surfaces. And as you might think, it makes a huge difference whether we consider mountain areas, urban areas, or some other complex structures. Another very important information are, of course, the source types. So there are three major source types, a point, line, and area sources. For example, a point source could be a smoke chimney, or like a line source like a road or highway, and an area source could be a forest fire. And for me, the interesting part, which was actually new to me, because I have a mathematical background, I had no idea about physics, to be honest, is the field of metrology. So I brought up two examples. So on the left, how does that work here? Oh, so on the left, you can see an alpine area. And the meteorological conditions change significantly during day and during nighttime. So we have anabatic upslope flows during day because the sun heats up the air close to the surface and causes unstable conditions. On the other hand, we have katabatic downslope flows during nighttime because the air close to the surface cools down and causes stable conditions. So this slope flows was a current project of myself, and the paper is currently under review, so cross the fingers please for me. But if we want to extend it later to urban areas, what's the goal of my PhD, we faced another different problem. As you can see here on the right, we have laminar flows over the rooftops. But we have turbulent ones inside the street canyon. So we can't use the models, what we performed in Alpine regions, also in urban areas. So we have to do a new modeling. So long story short sense, this was a short introduction about the different influences, and now we'll just ride through into the models. So in the Gaussian, the Gaussian plumb model, is described by advection, diffusion, and deposition. So advection is basically the transport of a substance. The diffusion describes the spreading from a source And, well, the deposition is quite difficult to model. So the deposition in general describes the process where particles set down onto surfaces, like the ground or rooftops, okay? And now the interesting part is what mathematical equation has this all in one? And the answer is it's the second-order partial differential equation. Don't worry, I will not outline it. But we will consider the solution, because the solution can be described in 3 dilution mechanisms. So the dilution in x direction is the result of a non-random process. So it only depends on the emission rate, so Q, and on the average wind speed. So for the crosswind direction, the dilution is caused by turbulent eddies. So if the dilution is a result of a large number of motions, and each having a neglectable effect of the concentration profile, then the crosswind direction follows this Gaussian probability density function you can see here. And also for the other direction. So if the dilution is unbounded, for the vertical direction follows also this Gaussian probability density function. So quite nice formula, mathematicians love it, but we look at the picture now. Well, the first equation is just plug everything from the last slide into one equation, quite fancy. But the interesting part is the picture here on the bottom. So as you can see here on the down, the sigma values indicate the rate of the plumb spread in both directions, so in y and z direction. Okay? And now we have to focus about I work in air dispersion modeling for an alpine region. So this formula is only valid for flat terrain. So we have to rethink this equation to use it in our setting. But I will talk about that later. Don't want to spoil. So to the second model, well, the second model is the stochastic Lagrangian particle model. It includes randomness, and, well, it assumes that each source emits a large number of particles, and each particle follows a random path. So the underlying mathematical theory is the Brownian motion. So Brownian motion describes the random motion of a particle into a medium. And what we want to do at the end is to track the particle's location so that we can pose our concentration profile. Nevertheless, again, some formulas for you. So this is a stochastic differential equation, whatever is standing there. So maybe the first term is the drift one, the second one is the diffusion one. Nevertheless, if you don't understand what's written there. But this is a linear stochastic differential equation. So there is a solution. And this solution is quite important because we simulate this equation every time step delta t. And then we use the Eulerian method to find the particle's location. Okay? So we have some other formulas as well for the other 2 directions. I will not outline because they are way longer. Nevertheless, remember just we use the second formula for the simulation and the last one to find the particle's location. And that there are other 2 equations for the other 2 directions, of course. Okay, now maybe to the applied part. So we, on the left, yeah, this is left here. So on the left, you can see a weather station we use. And on the right-hand side, you can see the interpolated wind field. So we use the inverse distance weighting method to generate our wind field over our whole area. But I will talk about that in a minute. And, of course, we have some data. This is, the first is the wind speed, and the second, the temperature from the weather station in Iverstein over 1 week. And what you can see with bare eyes is that, of course, for example, down there, the temperature increases during the day. And we use this data as an input for our models. Okay. So basically, we have 13 measurement stations over our area, and the area is about 27 times 9 square kilometers. and the height above sea level ranges from 500 meters to 900 meters. So we have distributed this weather station around the whole area, and, well, for better understanding, we have 30 measurement stations, and what we need for the simulation is a whole wind field. So wind speed, wind direction, temperature, pressure, and all other physical and meteorological parameters. And to do this, we use this inverse distance weighting method. And the basically assumption is that the value of an unrecorded point is the average of, or is the weighted average of a known value in the neighborhood. Okay? So the weights are somehow related in distance from the predicted one to the sampled location. Okay? Yeah, point. Good. Now maybe a little about the coding. So as you can imagine, it's quite hard to implement these two models in our topography. I will start first with the input. So you saw this equation, you saw these variables. We calculate them in the first step using some equations also. But after having modeled this wind field using the inverse distance weighting method, we have still the problem that the mass conservation law is not fulfilled. And that's a huge problem. So we use the SAW function here at the top right. Or how should I say that? We try to formulate an optimization routine so that the original wind field changes as less as possible from the new one, but with respect to the restriction that now the divergence is almost zero, so that the mass conservation law is fulfilled. So it's a quite tricky part. Nevertheless, after we are successful with the first, we go right into PM. So PM is the particle model, stochastic Lagrangian. First of all, we calculate the deposition process, therefore we need the deposition probability, because we say if a particle touches the surface, it might be either deposited or reflected. And now the interesting part is at the second function call, because to run this particle model, we use this formula I presented you before for all three directions and find the particle's location, but we also have to calculate the reflected path. And that was quite tricky because we use a lot of geometrical analysis I definitely will not outline. So this was very tricky. To the last one, so we use a kernel function, actually, which is from Gaussian nature, to calculate the concentration profile from the position of the particle. So this is just the last step to really finally have this concentration profile. So this is basically the idea for the stochastic Lagrangian particle model. And now to the second one. So the first part doesn't change at all. So the input is for both models the same. But afterwards, maybe I describe the idea first. So the idea is to fit this Gaussian plumb equation I mentioned before, which is for flat terrain, into a dynamic system. Our motivation to do this dynamic Gaussian plumb model is the fact that the computational burden of the particle model increases linearly with the number of particles also increase. But this dynamic Gaussian plumb model does not scale at all. So the computational burden would stay constant. And that's actually what we want if we also want to switch the model into urban areas where we have more sources. So remember, the Gaussian plumb equation provides information about how much concentration is transferred from a central point to the surrounding. So for the first function call, let's assume depending on wind speed, wind direction, and the other amazing things. Each point in our air volume has this Gaussian plumb. So remember the shape of a megaphone. And then we can look where this plumb crosses another point and mark this point. Then we can look in each plumb. Where this marked voxel appears, how much concentration it receives from the central one. And if we write this in the correct way in our three-dimensional field, we can interpret it like a filter mask. And this is the idea of the dynamic system, because we have parallelized processes behind it. This happens in the first function call. To the second one, so in the model before, I described, okay, we can use geometrical analysis to calculate the reflected paths, but this can't be done here. So we have a grid, we have subgrids, so we have rectangles. There is no reflection path of a particle. But one idea is that we downweight. So for example, we have here this plum, and here in the middle is a mountain. Then we can downweight the concentration behind this mountain and set it in front of. And that's basically the idea what I'm currently working on. And of course, if we do this switch, we have to do some normalization so that no concentration is missing. Okay, this was a main idea thing about the last part. So this model is currently my work, what I'm searching about for answers. So for better understanding, I prepared a simulation for you. Hopefully that works, okay. So what you can see here, so the first two pictures describe the soil pollution. On the left, there is always the dynamic Gaussian plum model, and on the right, there's the stochastic Lagrangian particle model. And this is the used topography we have, and here on the cross, there is the location of the chimney. And here you can see the different boundaries, so the north, the east, the south, and the west. Before I click on play, I, of course, speed up the dispersion a little bit. Okay, so it's not that quite quickly in general. Okay, so here is the chimney, and then you can see the spreading. So maybe for a short stop. So the red denotes high concentration, and kind of a gray shade is lower concentration. And you can see that caused by wind speed, wind direction, temperature, you can focus that it will go to the northern boundary. Maybe just a little bit more. Okay. So you can see here that here is something on the north. And here on the bottom, you can see you're right, what you see in the first one. Okay? So what we want to have is later in the future. So currently the deposit. Okay, I mixed up. Oh, here. Smart moment of myself. So what we actually want to have in the future is that the deposition process works as well. So currently this looks quite fancy because in the air the spreading works quite well. But we can't, or we didn't fix the problem with the ground, so we don't know how much pollution is actually set on the ground. We just know, okay, the spreading in the air looks quite good for our modeling. No, God. So no. Okay, just quickly continue. So we still have a lot of open questions. So if you're excited into air dispersion modeling, we can have a very good chat afterwards, because this topic is so important for the future. And well, at the end, I just want to thank all of you. Thank you.
Iris, thank you a lot.
Yeah.
Very great talk, very interesting. I would also have a question for you, very small one. For these measurement stations that you had, were you able to plan them, so to do a design, or did you just take them because they were already there before?
No. Oh, okay, yes, there was a no-yes question. Yes, they have been there already before. Okay, so my supervisor and his colleagues are planning this, and when I was coming in 2020, the weather stations are also installed, so I've done nothing.
Okay, yeah, okay. Good to know. So thank you a lot again. Good luck for your PhD,
Thank you.
We will see you later in the Q&A session.